And I think that hybridization is kind of lame, but it's something that you have to know anyway. So let me pull up this whiteboard so I can show you. So if you remember from any of your math classes, everything, like if you were doing a problem that was like x plus 3 equals 10 and you'd have to solve for x, there's an understood 1 up here, and because it's understood, we don't write it out. It's the same here for our s and our p orbitals. So the reason it's SP is because it's S1, P1. So there's a more sciencey like reasoning for this, but I'm really bad at explaining it. And this is how I remembered it. I think it's really handy. So if you have 2 regions of electron density, you need these superscripts to add up to 2. In the same way, if you, okay, so you'll only ever have one S. S will only ever be 1. You'll never see a subscript or superscript up here. P can go up though. So if you have a molecule that has 3 regions of electron density, what should P be? P what?
2.
Yes. So you're just adding these superscripts together. Does that kind of like make sense?
Mm-hmm.
Okay, awesome. So, okay. I'm doing handout 14. So just to kind of start off, we talked about formal charge. We did some formal charge last time, but how would you calculate formal charge?
Don't you take the valence electrons minus the bonds and the pairs?
Yes.
Or like plus those 2?
So formal charge is equal to valence electrons minus number of bonds minus non-bonding electrons. And I believe it was non-bonding electrons divided by 2, right?
It was a half, yeah.
Okay. Okay, so what is a resonance structure? Anyone? It's not like really a huge deal, but you should know what it is, especially if you are pre-med or pre-vet or anything that has to go into organic chemistry, because resonance structures are going to come back with a vengeance. So a resonance structure is, so its purpose is to show the movement of electrons. Specifically, we're going to be talking about the movement of electrons between double and triple bonds, because if you remember when we drew nitrite, right? Yeah, nitrite out, I asked you what is another way you can draw this, and we just put the double bond on the other side. So that's exactly what it is. Oh. So what about a resonance hybrid? So think about resonance. So we've discussed what a resonance structure is. What is a hybrid? Like, if you have a hybrid car, what does that mean?
It's electric.
Yeah, so it's electric, but you can also use fuel, gasoline, right? So you're taking two things and you're putting them in one, which is exactly what this is doing. A resonance hybrid is depicting both of the resonance structures at the same time. So this is also a truer depiction of the molecule because those electrons are not just choosing one double bond to stay at, they're constantly bouncing back and forth. So resonance structure depicts all, a resonance hybrid depicts all resonance structures in one drawing. And this is a truer depiction of the molecule. Okay. Draw the Lewis structure for the nitrite ion. Calculate the formal charge of all atoms in the molecule. So I'm going to go back to my whiteboard. Okay, so what is the formula for nitrite?
Is it NO2?
NO2 what?
-2.
It's going to be minus. NO2 2 minus is going to, no, that's a lie. It is 1 minus. And then nitrate will be NO3 minus. So we're just going to draw a plain old Lewis structure. So what's step one?
Find the valence electrons.
So nitrogen has 5 and we only have 1. Oxygen has 6 and we have 2. And then we have an electron, which is giving us 1. And I'm getting this from this charge up here. So it's going to be 12 plus 5 is 17. It's going to give us 18. So now we're going to draw it out. We're going to attach our oxygens. I know we did nitrite yesterday. It's just a relatively easy one to show that does have a formal charge on an atom. So how many electrons have we used up so far making these bonds?
4.
4. So now we have 14 left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 14. So we've used all of our electrons, but nitrogen doesn't have an octet, so what are we going to do?
Make a double bond.
Make a double bond. So I'm going to go with the right oxygen, but really it doesn't matter which one you use. So everything's happy, everything has an octet. And now we are going to find formal charge. So let's start with this oxygen here. Oxygen has 6 valence electrons. We have 2 bonds, 4 in bonds. I made that mistake yesterday. And we have 4 non-bonding electrons divided by 2 is 2.
Which one are we doing? Nitrogen?
This one.
So you subtract 6 from 4 and then divide by 2, or?
Someone help me out here. Because this, oh, you know what? I'm doing it on the wrong one. This is right. There is no formal charge here. And then, sorry, I was stressing myself out. So for nitrogen, we have 5 valence electrons. We have 2, 4, 6 and bonds. And then we have
3.
3. Then what did I do here?
No, you do
Okay.
2 and minus 3 because then that equals 0. Because you have 2 lone pairs on nitrogen. And then minus 3 because there's 3 things attached to it.
3 bonds. Okay.
I'm pretty.
So, this is weird. Because I've always worked with a different formula for formal charge than what she gives you, which is why I kept like messing it up yesterday. Because I always did the number of valence electrons minus the number of bonds minus the number of non-bonding electrons, so there's no division at all. So the way that I would do it is there's 6 valence electrons, we have 2 bonds there, and then we have 4 non-bonding electrons. And that's how I would do it because I don't like adding division into things. So are you guys cool if I use that one? Because I keep like screwing up the divide by 2, whatever. Like, is that cool?
Can you go over how that equation works again? So you do the 6 minus,
Yeah.
and then what do you do?
So the way that I do it is, so if we're looking at this oxygen here, we have, so oxygen has 6 valence electrons. We figure that out based on the periodic table. And then I look at the number of bonds that it has. So we have 1 bond here and 1 here. So we have 2 bonds attached to it. And then I look at the number of non-bonding electrons, not pairs, but the number of like individual dots, which here's 1, 2, 3, 4. And then you subtract 4. 6 minus 2 is 4. 4 minus 4 is 0. Does that make sense?
Oh, okay. Okay, yeah.
So then up here, this is the same thing, only I would have flipped the 2 and the 3. So you have 5 valence electrons, 1, 2, 3 bonds attached to nitrogen, and then 1, 2 non-bonding electrons, which gives 0. And then for this oxygen here, oxygen still has 6 valence electrons. We have 1 bond, and we have 1, 2, 3, 4, 5, 6 electrons not in bonds. So that gives us a -1, and so this has a negative right there. So let me like erase all of this so that it's not so messy. So this is how you would draw that. You can put the formal charge on the atom that has that charge, or you can do nitrogen. Draw out the structure and then put it in brackets and put the charge up here. So those are your 2 options. Usually she's going to want you to do the brackets and do this up here, but this is correct. And if it's a free response question, which I don't totally know how that'll work out now, but if for any reason you have to draw it, either of these are acceptable. Okay, any questions there? Okay, so looking at this here, the next question is give an appropriate resonance structure. So how would we draw a resonance structure?
Just flip.
Yeah, we're just gonna flip it. Just have nitrogen, but our single bond is going to be over here with the formal charge of -1. And then over here is where we're going to have our double bond. These are resonance structures. So, the next question is to draw a resonance hybrid. So how am I going to create a resonance hybrid for this? So we are going to use dotted lines, which means we're going to connect an oxygen to each. We're going to put all of the lone electron pairs, but here's the thing. So remember how on the normal Lewis structures we would have 6 electrons on one and then 4 on the other? Now they're both going to only have 4. And I'll show you why. And so to depict both of those resonance structures where they're mirrored in the same drawing, we're going to use a dotted line. And that's going to make each of these oxygens have -1/2. Because then when you add them together, that gives you a -1, which is the overall charge of the nitrate, or nitrite ion, sorry. So they each have a -1/2, but you don't have to do that. As long as you remember you're working with nitrite and it has a -1 charge, you can just do that. That makes sense.
Yeah.
Okay. So next question. Let's go ahead and erase this. So what is the electron domain geometry of nitrite? Oh, shoot. Okay. What is the electron domain geometry of nitrite? Start by identifying the number of regions of electron density. How many regions of electron density does it have?
Two.
3.
Oh,
But
three.
yes, you're close. So it has 3 regions of electron density. Where do 2 come from?
Is it the oxygen? I don't.
So,
Or
okay.
is it sorry.
No, you're good. You're good. Go ahead.
I was gonna say, is it from S, I think? Or sorry, P. Is it from P?
You're good. It's going to come from the 2 bond regions. And 1 from the lone electron pair on nitrogen. So whenever you're looking at this, you're always going to want to focus on the central atom. So let me go ahead and pull up that whiteboard again. So we're looking at our nitrogen, or our nitrite. So whenever we're looking at like electron domains or electron density regions, we're going to be looking at the central atom, so our nitrogen. So a lot of people are really tempted to go based on number of bonds and to say there was 1, 2, 3 bonds and 1 lone electron pair, so there's 4 regions of electron density, but that is not right. Double and triple bonds are going to count as a single bond would. It's still going to count as 1 region. So here we have 1 region, 2 regions, 3 regions. this molecule is not possible unless you change the charge, but if you were to have something that looked like this, how many regions of electrons?
4.
4. Because you're going to have 2 from bond regions and then 2 from lone electron pairs. Does that make sense?
Yes.
Okay. And there's more of this in the worksheet, so we'll still get more practice with identifying these things. So, okay. So we have 3 regions of electron density. So what is our electron domain geometry?
Would it be bent? Or
You are not wrong because that's your molecular geometry.
oh, okay.
So the electron domain geometry is trigonal planar,
Oh, okay.
and the molecular geometry is bent because you have one lone electron pair. So the full geometry, if she just asked what's the geometry, it's going to be trigonal planar bent. And the reason you have to specify that it's trigonal planar is if you look at your handout, if you go to 4 regions of electron density, so tetrahedral, and you go down to 2 lone electron pairs, that one is also bent. So you want to specify the electron domain geometry as well, because some of those things do repeat themselves. Yeah. Okay, which elements are satisfied with the sextet? So what is a sextet? We also went over it yesterday. Yes. Boron is the really big one, and then the other one is beryllium. But boron is definitely the biggest one that you would most likely see. Okay. So up next, draw the Lewis structure for CH3F and label any polar bonds in the molecule. So how do you guys feel about polarity, polar bonds, that type of thing?
I don't really understand that.
Okay, that's fair. So CH3F, we have C, which has how many valence electrons?
4.
4, and we have 1. Oh. Hydrogen has 1, and we have 3. And then fluorine has 7, and we have 1. So 4 plus 3 is 7, plus 7 is 14. So what's going to be our central atom here?
Okay, how do you know what this is? Yeah, that's what I have a question on that. I don't know.
Okay.
how you determine what the central atom is.
So in this, I'm trying to remember which rule it was from drawing Lewis structures, but hydrogen and the halogens are often going to be your terminal atoms. Whenever carbon is present, it's going to be your central atom because carbon looks like this. So it can accommodate 4 bonds. So it can accommodate like the maximum number of bonds. And because you have this, if you go on to take organic chemistry, you can make these long, super long chains of carbon that just go on forever and ever, and you can just attach even more things to them. Does that make sense?
Yes.
So here, carbon is going to be our central atom, and we're going to attach everything else to it. So we have 3 hydrogens and 1 fluorine. How many electrons have we used?
8.
8. That brings us down to 6, which is just enough to fill up our fluorine. So that's done. Remember, we don't add any onto hydrogen because hydrogen can only have 2 electrons, which are held in this bond right here. So they're already at their max. Okay, so going to polarity and polar bonds, do you guys remember talking about electronegativity in periodic trends?
Yes.
Okay. So looking at your periodic table, what is the most electronegative element?
Fluorine.
Fluorine. It's going to be up here, and it's going to decrease going this way, and it's going to decrease going down. So that means that if you look at fluorine relative to carbon, which has the higher electronegativity?
Fluorine to carbon.
Fluorine. Yeah, fluorine to carbon.
Fluorine.
Fluorine. And you'll denote it like that. So because carbon is further left to the periodic table than fluorine is, fluorine has the higher electronegativity, meaning there's a difference there and there's a pull. One thing that may be a little weird because hydrogen is all the way to the upper left of the periodic table, carbon and hydrogen is considered a non-polar bond, which is kind of like a weird concept, but that's just how it is. And again, that really ties into organic chemistry and things that sort of go beyond the scope of this class, but they teach it to you anyway.
Sorry.
Go ahead.
Does fluorine have to be at the top?
No, it can be.
So I didn't know if like the arrow mattered, what way you draw it and stuff.
No, I mean, you could put this anywhere. Like if it were down here, you would just draw the arrow going towards fluorine.
Okay.
Yeah.
Good.
So the polarity depends on like how high the electronegativity is?
Yes, exactly.
Okay. Okay.
Yeah. So this isn't in the handout, but if you had, sorry, if you had hydrofluoric acid, which is HF, it would look like this, and your polarity would look like that. I keep using fluorine just because it's what shows up most, because it's the most electronegative, it's the easiest to remember. Fluorine with anything, fluorine is going to be the polar bond.
Could we do an example without fluorine?
Yes. So let's take carbon dioxide. Okay. So this is a little bit of a hard concept for some to grasp, but carbon dioxide has polar bonds, but it's a non-polar molecule, and I'll show you why. So we have C. So carbon is 4, oxygen is 6, times 2 is 12 plus 4, 16, 2, 4. And then, okay. So look at carbon and oxygen on a periodic table. Which one is closer to fluorine?
Oxygen.
Oxygen. So that means there's going to be a pull towards the oxygen because it has a higher electronegativity. So this is a polar bond, and then this is a polar bond. But do you notice how they pull in opposite directions?
Mm-hmm.
So they cancel each other out. And that's why overall carbon dioxide is nonpolar, but it does contain some polar bonds. Does that make sense?
Mm-hmm.
It's like if you're playing tug of war and you're both tugging with the exact same strength, that rope's not going to move.
Yes.
So does this help with polarity and sort of understanding that?
Mm-hmm.
Yeah.
Awesome. Okay. So going back, do you guys still see the whiteboard, or do you see my handout?
Whiteboard.
Okay. Okay. So what is the electron domain geometry for that molecule? How many regions of electron density are there?
4.
4 regions of electron density. And all 4 of them are from bond regions. So we have 4 regions of electron density. What does that make our electron domain geometry?
Tetrahedral.
Tetrahedral. And just for fun, what is the hybridization?
Shit, what's hybridization again?
How many regions do we have?
Oh, 4.
And one is automatically taken up by S, right?
Yeah.
So what does the P superscript have to be? To add up to 4?
Oh, 3.
3. Another way that you can do this that I really like is if you have the molecule drawn out. So CH3F. Is what I do. If you do this, I recommend erasing it. I don't know if she'll like get angry over this, but this is a nice little trick, and it's the same thing only you're drawing it all out. Is I just go through and I label each of the bonds. S, P1, P2, P3. Does that help?
Yes.
Okay. Okay. So the next one is to draw the Lewis structure for ICl3. What is the formal charge of I? Okay, yeah. we have time to do this. We have iodine trichloride. How many valence electrons does iodine have?
7.
7. What about chlorine?
21 or 7, but times
Yeah.
2.
7. 7, but there's 3, so that makes it 21. So we get a total of 28. What is going to be the central atom?
Iodine in the middle.
Yes. This is a bit weird because they're all halogens, but whenever you have one of something and then multiple of the other, it's usually easier to like stick the one that's different in the middle that you only have one of. So we use 6, got 20 here. 12, 14, 16, 18. So I have 4 electrons left. What am I going to do?
Put them on the iodine.
Yes. Okay, so that is our complete structure. For formal charge of iodine, you have 7 valence electrons. How many bonds do you have?
3.
3. 1, 2, 3, 4. Nope, 3. And how many non-bonding electrons?
4.
4. So it's just a formal charge of 0. There's no charge on this. Are there any polar bonds in this molecule?
Yes.
Yes, but they're all canceling each other out. Because chlorine is closer to fluorine than iodine is. Okay, how many regions of electron density does this have?
5.
5. 3 from bonds and 2 from one electron pairs. So we have 5 regions of electron density. What is our electron domain geometry?
Trigonal pyramid. Bipyramid.
Yeah, trigonal, bipyramidal, or bipyramid, whichever. Right. Okay. So next up, we are taking a look at CH2O. So with the carbon, we have 4 electrons. These have 1, but we have 2 of them. Oxygen is 6, so 10, 12. We're gonna have C, H, H, O. You can put these in whatever order you like. Just how I end up drawing it, because I already know the geometry of it. So we've used 6, so now we have 6 left. And they're going to go on the oxygen because hydrogen can only have 2. But carbon always has to have that octet rule, so we have to make a double bond. Okay. How many regions of electron density does carbon have?
3.
3. So what is the electron domain geometry?
Trigonal planar.
Trigonal planar. What's the hybridization?
Trigonal planar.
The hybridization.
Wow, okay. I keep forgetting.
So what do we start out with?
3.
Yeah, so we have 3 regions. S automatically takes up 1. So how many P do we need?
Oh, 2.
2. S, P1, P2. Okay. So the last Lewis structure that I'm going to make y'all do, I promise. So I know these get kind of tiring. Is going to be sulfur hexafluoride. So sulfur gives us 6 electrons. Fluorine gives us 7, and we have 6, so that's 32. I don't remember.
I think it's 42, so it'd be 48.
42, yeah. Thanks. 48. So we're going to have sulfur in the middle, and we're going to connect 6 fluorine. So we used up 12. It's going to give us 36. And 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Okay, how many regions of electron density do we have?
5, 6.
6. What's the electron domain geometry?
Octahedral.
Octahedral. It's really weird because there's 6 and it's octa, but it is octahedral. What's the hybridization?
sp3d2.
Yes. 3 is the absolute max on the P. So once you hit that 3, you have to move to D. So we have S, P1, P2, P3. We have to move to D, D1, D2. Does that make sense?
Yes.
Okay, awesome. So that's the last of that. Okay. How do electron domain geometry and molecular geometry differ? What's the big difference in like figuring out which is which?
Oh,
So do you remember when we had that molecule that was trigonal planar bent? Why did we add bent onto that?
To like say what it looks like.
Yeah. So how did we figure out that it was bent?
Because of its electronic geometry.
Yeah, so we look at the electron domain geometry and then we look at the number of lone electron pairs, right? So, okay, this is kind of wordy, so I'm gonna type it out and then read it. Okay. The electron domain geometry considers those bond regions and those lone electron pairs to have the same amount of repulsion. It doesn't really differentiate between the two. Whereas the molecular geometry looks at the number of lone electron pairs that you have, and lone electron pairs are going to have a higher repulsion than those electrons in the bonds. They really just don't want to be messed with. They take up a ton of space. So they're going to have an impact on how that molecule is actually going to look. Does that make sense?
Yeah.
Okay. So true or false, you can determine bond angle from electron domain geometry.
From
True.
False.
Oh, false. Okay.
So I'll tell you why. And it goes back to this statement here. Lone electron pairs have stronger repulsion than electrons in bonds, meaning they're going to push these bonds further away. And it's going to change the amount of space between those. So okay. And lastly, what is the bond angle of a tetrahedral molecule? So one thing I want you to notice is on your sheet, whenever there are no lone electron pairs, the molecular geometry is exactly the same as the electron domain geometry. So when I say tetrahedral, I mean like tetrahedral, tetrahedral, but we don't say it twice, we only say it once. So if they're asking you for a bond angle, you can assume that this means there are no lone electron pairs and that the molecular geometry is tetrahedral. So what is that bond angle?
Oh, 10 or 1.
109.5 degrees. What do you think is the most common wrong answer to this question?
110.
110, that is true. 110 is a common one. Another one, so if you're one of the people that don't memorize it and you're like, oh, I'll just do the math, 360 is a circle, 360 divided by 4 is 90. 90 degrees is a really common wrong answer. And in theory, you would think it would work out because you're dealing with this circular space that's 360 degrees, cut it up into 4. But the reason that that's wrong is, I'll have to write it out because I've worded it much better in here. Okay. So the reason it's not 90 degrees is because we are dealing with a three-dimensional space, meaning we're dealing with a sphere and not like, I don't know if you guys have taken pre-cal or trigonometry or if you took any of that in high school, but a really big deal is the number wheel and whatever. And I vividly remember getting this question wrong because that's what I thought about. I was like, oh, I'll just divide by 4 because I don't remember. And I got it wrong. So I'm stopping you guys from making my mistake because we're dealing with a volume, so like a tennis ball rather than this flat just circle. Does that make sense?
Yes.
Okay, awesome.